Okay, so hi everyone. As mentioned, today I'll be talking about bootstrapping fiber orientation distributions. And first of all, just to explain what fiber orientation distribution functions, or FODFs or FODs, as they're used interchangeably, what they actually mean. So they are these little bow shapes or little butterfly shapes that one can get per voxel. So they're basically extracted from diffusion-weighted MRI signal, and they provide information about microstructural organization of the image tissue fibers. So it's on a subvoxel level, resolution level, and this opens up the opportunity to track the fiber streamlines using the so-called tractography algorithms. So the problem with there we go. So diffusion-weighted MRI is an inherently noisy technique, and this results in a certain level uncertainty tied to the estimation of ODF. So if you sample the signal multiple times and then estimate the ODF, this is always each time a little bit different, and this manifests in different local maxima orientations represented by these colorful lines, which leads to this sort of the cone of angular uncertainty, which is what most of the probabilistic tractography algorithms have been focusing on so far. But the fact is that this leads also to the variation of the entire shape of the ODF, which can be represented by so with this results in shape uncertainty represented by the mean amplitude per vertex of the ODF and its standard deviation. So this uncertainty is especially important in the context of tractography, because it has been shown by studies that this uncertainty propagates errors in the tracking of streamlines. So instead of nice tractograms like these, you get something more like this, with lots of false positives. And even though this is good enough for a rock band, might not be good enough for neuroscientists and neurosurgeons who want to use this method for neurosurgical planning. So how can we measure this uncertainty? One way is to use the most conventional, so the so-called true bootstrapping approach, where you acquire repeated diffusion MRI data sets, and you acquire the diffusion signal. So these little green shapes is how the diffusion signal would look like in a 3D space. And then you randomly select individual diffusion direction measurements to form a set of synthetic diffusion data sets. So if you do 600 bootstrapping runs, you get 600 synthetic diffusion data sets. Then you apply the any spherical deconvolution method to estimate the bootstrapped fiber orientation distributions, and you obtain information about angular uncertainty and shape variability. But because of long imaging times with repeated acquisitions, the residual bootstrapping has been proposed, which is actually model-based. So you use ordinary least square fit of spherical harmonics basis functions to the signal to sort of get an estimated signal from which you can then compute the residuals, and then you resample the residuals rather than the actual diffusion measurements. Okay, so these are the two methods that I have been focusing on, and we will look at of how to measure uncertainty. But how do we quantify uncertainty? So as I mentioned before, you can focus on the angular uncertainty, from which you can obtain an uncertainty ODF, which is basically a diffusion a density function of all the identified local maxima. Or you can look at the entire shape variation, and you get shape uncertainty represented by mean ODF and standard deviation. So in my simulation experiment, the first step was to simulate signal for two crossing fiber populations at challenging fiber configurations. We used the 3 different angles, and also I've added the isotropic compartment with quite a large volume fraction, which makes it much more challenging to then sort of disentangle the orientations of the fibers, and using relatively low SNR of 15 and 10. So with the given isotropic compartment, this makes the effective SNR even lower. And then the next step was to quantify uncertainty, as explained in the previous flowchart. So just looking at the results of the single case, we can see that a single ODF estimation without any bootstrapping shows results that are worsened as you lower the SNR and the actual angle, crossing angle of the fibers. And then looking at the residual bootstrapping results, we see that they're actually not much different. So uncertainty ODF is just the same as you move to the low crossing angles and low SNR. You get something, the local maxima directions which are almost by 90-degree angle off for one of the fibers. And looking closely at the shape uncertainty mean ODF, it's actually no different than the single ODF estimation without any bootstrapping. So this might suggest that using the model-based approach of bootstrapping, residual bootstrapping based on spherical harmonic signal decomposition might not be the best approach of modeling the actual noise that you get, the white noise in the signal acquisition, because uncertainty is in the estimation of ODFs is a result of both the failures of the incomplete modeling of the signal, but also the noise and any potential artifacts in MRI acquisitions. Looking then at the true bootstrapping results, we see that the ODFs are actually much better aligned with ground truth. Uncertainty ODF does give a bit more false positives, and shape uncertainty gives sort of a smoother profile and a bit flatter as you move into the low SNR and low angle region. Okay, this was very quantitative, but looking more at the qualitative results, qualitative, moving to the quantitative results, we can see that the root mean square error of the angular error of compared to ground truth of uncertainty ODF is much more unstable, which is represented by the red plot on this graph, and the error stabilizes relatively quickly for the true bootstrapping, the bottom 2 plots, which is already at 50 bootstrapping runs. This requires very, very little computational power. But more importantly, we see that the angular error is consistently higher for residual bootstrapping. And just using 2 signal acquisition repetitions, this error is halved and brought much closer to 10 signal acquisitions, which is sort of a gold standard. And looking at the shape divergence of the ODF, mean ODF from the noiseless ODF, which again is sort of a gold standard, we can see, so first of all, just to mention, this was measured by Jensen-Shannon divergence, so as a metric for a shape dissimilarity of distributions. And the units are in nats, which is a unit for information, similar like bits, but based on natural logarithms. So the residual bootstrapping shows, again, is consistently higher in the shape divergence from the noiseless ODF. And just using 3 or 4 repeated signal acquisitions is already quite close to 10 signal acquisitions, and you don't get much more improvement from there on. So just to summarize this, okay, so we noticed that single FOD, fiber orientation distribution, is relatively tricky when you get to low SMR and low crossing angle. And residual bootstrapping actually gives the results that are not much different. And true bootstrapping provides the results that are much better aligned with the ground truth. But you might think then, well, yes, that makes sense because you use 3 or 4 times the amount of data. How is that any different from signal averaging? The answer is it isn't. So if you just average the signal first and then you do a single ODF estimation, you get very similar results. But there is one extra bit of information that you get from bootstrapping, which is this little cloud around the ODFs, providing information about shape uncertainty. The question is, though, can we use this shape uncertainty information to threshold the fiber orientation distribution for the tractography? And yes, we can if we take the coefficient of variation per vertex of the ODF represented by this sphere, and then you decide to discard anything that is in the region where the coefficient of variation is higher than 1. And so then if you filter the ODFs, we can see that we get rid of the false positives in true bootstrapping. However, in residual bootstrapping, again, there's not much improvement. The takeaway message here is garbage in, garbage out. So if you start with bad data, no amount of noise modeling or filtering will be able to salvage this. We also confirmed this with the tractography simulations using the probabilistic tractography algorithms based on residual bootstrapping and then true bootstrapping combined with CV filtering, and we see there's a much higher proportion of correct streamline trajectories with true bootstrapping and CV filtering, and less connections lost, which are represented by the blue connection streamlines here. These are the connections that end prematurely, and there's less false positives, the green ones which end at the wrong target, basically, because they're pulled by the crossing fiber bundle at the crossing region. So just to quickly summarize, shape uncertainty is more stable than uncertainty ODF.
We're actually over time.
Thank you.
So unless there's a burning question, we'll just move on to the next speaker. And thank you very much.
Thank you.